I hope that you've already watched my video called Working with Units. And this video is going to be Working with Units Part 2. And the purpose for this is anticipating that you've been in the thermodynamics class now, maybe for a couple of weeks, and you're starting to see some repetitions in the importance of using units and repetition of some specific conversions uh, that are needed to be used in problem solving. And you're starting to see, oh, this is happening again and again. And I think I need some reinforcement or some reminders of some of the most important parts of using units throughout your problem solving. So let's get started. So this is part two, some selected tips that I'd like to share with you about some things that I'm finding a lot of students come in with really good questions about, maybe not exactly confusion, but maybe discomfort in how do I use this, how do I use that? And that's why I've selected a set of about 5 tips for this video. So just as a reminder from my first video, working with what I call unity is a key to success. So a very easy problem that I think you can do in your sleep now, how many meters are there in 1.75 feet? Okay. And so the first thing is, okay, I need to convert feet into meters. I'll go to my one-page handout of conversion factors. And oh, okay, I see a conversion here. 1 foot equals 0.3048 meters. This is one that I have not committed to memory. So I've got to go to the page and write this down nearly every time. Now, so based on my Working with Units video, remember, how do we turn this conversion statement into unity? Well, we just take 1 divided by the other. And so it's unity. 1 is 1 foot divided by 0.3048 meters. Okay. Or similarly, unity, just 1 is 0.304 meters divided by 1 foot. So which do I use? Which do I use in problem solving? Well, I've got feet and I know I've got to cancel feet out. So pretty clearly, I'm going to use this expression for unity in my, let's say, homework problem. 1.75 feet times unity, and I cancel out, I'll strike out the feet and feet with my pencil, and sure enough, I do the math with my calculator, 0.533 meters, and so my homework answer is there are 0.533 meters in 1.75 feet. Really pretty easy, but this is going to be the basis for all the tips that I want to remind you of. Oh, right. I really, really want to stress the importance of your gaining a paper copy of this one-page conversion factors from your book. So this is where, of course, I got the length conversion. And let's see, very quickly, I'll remind you how you can get it if you haven't gotten it from some source or already gone to your book and just clipped out that particular page or somehow copied it if you have a paper book. Let's see. I've got to get out of PowerPoint. Yes, I'm out of PowerPoint. I'm going to go to my browser. Welcome to Jay's Toolbox Canvas site. Hopefully you've signed up to join the tutoring group. And let's go to Files. We'll click on Files, and come down to Tutoring, ME2134. And then there's 4 folders I've got in there. And so if you click on the Resources folder, you'll be able to possess this one page simply by clicking on the conversion factors file. And then you can, and there's that one page, and you can simply download that to your own PC and print it out on paper. So that's what I want to encourage you to do. Be sure to get a copy of that one-page conversion factors file. Okay, first tip. By now, I hope that you have in your head, more than just in a formula sheet, what's the difference between capital V and little v? Think in your head, Be real honest with yourself. Wow, what's the difference? What do I know is the difference before we go to the next slide? Difference between capital V and little v. Well, let's see. Capital V is the volume of a system, and little v is called the specific volume. I know the first couple of days in class, we talked about extensive properties and intensive properties, but certainly in problem solving, the big thing is remembering that capital V is volume, little v is called specific volume. So I hope you have all of these expressions in your head. V is capital V over M. That's the definition of specific volume. Or volume is mass times little volume. Might come in handy. It's the same expression, isn't it? Hope you have it in your head. And of course, density is the reciprocal of volume, or mass divided by volume. So I look right here. Here's a typo already in my slide. That should be M divided by capital V, shouldn't it? Density is mass divided by volume, kilograms per cubic meter. Okay, well, this kind of is a good way to look at units. When you have capital V, when you have volume, English units problems, of course, you should always be thinking cubic feet. If you've got cubic inches, immediately convert to cubic feet. In SI units, volume, cubic meters. If you're given liters or cubic centimeters, immediately switch over to cubic meters, just to make life easy on yourself as the problem solving process goes by. How about little v? Little v is going to have English units, cubic feet per pound mass. V over little m, cubic feet per pound mass. And little v, specific volume, in SI units, cubic meters per kilogram. So that's just a little refresher, but a lot of students at this point, even after a couple of weeks, can get capital V and little v confused. I'll bet you've got it pretty well in hand. Okay, next set of tips. What's a bar? What is KPA? What's PSI? What is ATM, atmospheres? Well, they're all measures of pressure, aren't you? You know that. You've got that nailed. Here's a pressure gauge on a tank. Okay, so all of these units are measures associated with pressure, or force over area. So a force divided by an area. Now, to make you feel a little better, in most upcoming textbook problems, except maybe for a couple, the given pressures moving ahead in many of our thermo problems, pressure is going to be absolute pressure unless otherwise stated. So unless stated as gauge pressure, you can be satisfied that when you're given a pressure in thermo class, it's going to be an absolute pressure. But let's look at units, because in terms of problem solving, and English units, and then we're going to move ahead to SI here in just a second. Well, jargon, PSI. In the working engineering world, PSI is what we use. We rarely, if ever, write down pounds force per square inch, but these are synonymous. A PSI is a pound force per square inch. Now, let's look at the next very important conversion. If you have 1 pound force pressing down on 1 square inch, how much force would be pressing down on a square foot? You can do this in your head. You know that there's 12 inches to a foot, and so a square foot is going to have 144 square inches to it. And so therefore this pressure conversion in English, 144 pounds force per square foot equals 1 pound force per square inch, 1 PSI. Okay. So another one ATM, commonly given in homework problems, engineering problems. That's a jargon for 1 atmosphere of pressure. And I hope that you have in your head. If not, you can go to your one-page conversion factors page to see that 1 atmosphere exactly equals 14.7 pounds force per square inch. 14.696, 14.7. In the engineering world, That's about the same. So back to our unity idea. In working through problems using unity to help yourself cancel units out, unity is 144 pounds per square foot divided by 1 pound force per square inch, or PSI. So in most of your engineering problem solving, whether it's homework or actual day job, engineering jobs, you're usually converting PSI into pounds per square foot. So that version of unity is going to help you out. Now on to SI units. Okay, pressure. 1 Pascal. So it's easy to forget what a Pascal is. Well, it's spelled out. Pascal, 1 PA is a Pascal. A Pascal is 1 Newton per square meter. That's just something you have to learn in your head quickly. That's something that I had to learn when I when I took thermo and we used SI units. So I was not familiar with what a Pascal is until actually late in my undergraduate experience. Okay, 1,000 pascals, 1,000 PA, 1,000 Newtons per square meter is 1 kPa, a kilo. K, that's like 1,000. So 1,000 pascals is 1 kPa, which usually you're given in your homework problems and also on pressure gauges. Pressure gauges typically are calibrated in kPa in the SI units. Okay. So let's see, we've got 1 atmosphere, 1 ATM is 1.01 bar, 1.01 bars. Of course, you can look this up or commit it to memory. And let's see. Oh, this was really important. I can't stress this enough. When you see a pressure given in bars, 1 bar, simply move that decimal place over twice to get kPa. Look at that relationship. So that's what reminded me 1.01 bars is simply 101 kPa. So in much of your problem solving, 1 bar. Also, common sense 101. 1 bar is just about, it's off by 1%. 1 bar is just about equal to 1 atmosphere. So it's 1.01 bars is 1 atmosphere. Okay, so back to our conversion factor practice. Unity is 100 kPa over 1 bar. But look, in the real world, in problem solving, you're going to write down, given 3.5 bars, given pressure, that 3.5 bars is going to be 350 kPa. So why are we messing with bars in the first place? Not commonly used in engineering practice. Bars are not commonly used in our engineering practice. Well, the reason that we do, the textbook has lots of thermodynamic property tables in the back of the book you're getting more and more familiar with. And so in the back of the book, the author has chosen to tabulate pressure in bars, not kPa. And so let's come down, let's just look at a pressure table for H2O, steam, water. Okay. And we'll come down here in our pressure column to 1 bar. And this is where in your head, when you see 1.00 bars, you're thinking 100 kPa. So this is just about equal. This is right at 1 atmosphere, give or take a little bit. Okay, those were first couple of tips. Now moving on to my third tip. Some students at this point are having a little trouble visualizing the difference between capital W out and little w out. And I can understand some reasons why, because in jargon, we engineers, we experienced engineers, we call both of those variables the work. We call both of them the work done by a system, the work done by a system, W out or little w out. And so some homework problems ask you, find the work per kilogram. Now, what does that mean? Let's talk a little bit about what the difference between capital W out and little w out is. First, for a closed system, capital W out and little w out. I hope that you're experienced sketch drawers now. So here is a generic sketch for a closed system piston and cylinder. Okay, little dash line, that's the system. The closed system is in there with fixed mass M, and it's going to go through a process from state 1 to state 2. Some work is done during that process. Heat is added during that process. And this is a pretty good sketch to sort of describe a typical closed system quasi-equilibrium process. Okay. And so both W out and little w out are commonly called the work done by the system. So what's the relationship between these variables? Little w out is capital W out divided by M, the mass of the closed system. So let's look at the units associated with work out, capital W out, and work out, little w out. Okay, first, capital W out in English units. It's a little bit of you might work in units of foot-pounds force through a distance, or English units might be BTUs, British thermal units. Either of those will work for units for capital W out. In SI, Newton meters of force through a distance, work out Newton meters. Well, a Newton meter is a joule. Wow, okay, a joule, a Newton meter. Got to have that in your head, okay? Or in many homework problems, you're requested to find the work done in kilojoules. You know that relationship. Now, little w out. So let's see, definition. Little w, that's the work out divided by the mass. So sort of by inspection, you can see that the units in English units are going to be foot-pounds force per pound mass. Of course, these do not cancel, do they? That's a force, that's a mass. Foot-pounds force per pound mass, or BTUs per pound mass. Either of those sets of units will work for little work out. In SI units, kilojoules per kilogram is what's commonly requested, commonly what you're expressing little w out for a closed system in your work. Now, you may have already been introduced to open systems. If not, I'll give you a little crash course in an open system. This is a schematic sketch of a turbine in which there is a gas flowing into a turbine with a rotating shaft, a gas flowing in. That same gas is flowing out at the same rate for this example. We call that steady state, steady flow. One inlet, one outlet. The rate at which mass is leaving this open system exactly matches what's going in. During the steady process, heat is added at a certain rate, and that shaft is rotating at a certain torque, and that's putting out power, shaft power from this turbine, and we call that W dot out. So notice here, if you haven't had a lot of exposure to open systems yet, here's your crash course. Notice how this is not W out, it is W dot. That dot is important. That's output power, not work. M dot is the mass flow rate, not the mass. Okay, M dot. M dot is going to have units, pounds mass per second in English, or kilograms per second in SI, M dot. So that's a big difference between M, W dot, big difference between W dot, power, and work, just capital W. Important definition now for what we're talking about. Little w for an open system. Little w for an open system is defined as W dot divided by M dot. This is really important. W dot divided by M dot. And so W out is also commonly called the work done by the open system. And I can see how students can really get confused, including myself when I was just starting out. Units of the variable little w out for an open system, all right? W divided by M dot. Let's look at SI first. Now, do you see that you can derive the units, don't have to be given it. Look, W dot, kilojoules per second. That's a kilowatt. Kilojoule per second, kilowatts, okay? Divided by mass flow rate, kilograms per second. I see that the seconds cancel. So the SI units for little w out are kilojoules per kilogram, not just kilojoules. English units, you can derive sort of the same idea and recognize English units for little w out, foot-pounds force per pound mass, and BTUs per pound mass. So see how the time units cancel in the numerator and denominator of the definition expression. So that's kind of an important thing. If you don't get anything but one thing out of this video, this part's really important. Okay, the next thing is I wanted to working with the units of W out and little w out are really, really important and sometimes hard to understand when you're just getting started. So this is my tip number 4. Okay. We're going to go through a number of examples. And so the first example, I want to say W out and let's just look at W out for a closed system. W out for a closed system undergoing a quasi-equilibrium process. In your head, without going to a formula sheet, if I said, you've got a closed system undergoing a quasi-equilibrium process, how will you determine the work done? W out, capital W out. How do you get that? It is my hope that without using a formula sheet that you have in your head from your practice and learning so far, for closed system, quasi-equilibrium process, W out is the integral of PdV, the area under the curve of a PV diagram. Okay. Well, let's look at units. W out, it's got to have units of kilojoules, or in other words, kilonewton meters. This is up in SI, kilonewton meters. Okay. Right-hand side of the equation, the units have got to match. Pressure. Let's look at pressure of kPa. Let's say that you're savvy enough to say, I'm going to use units for pressure of kPa. That's a kPa is a kilonewton per square meter. And units for dV, incremental change in volume. Well, that's going to have units of cubic meters. So if I put my volume units in cubic meters, let's cancel. Let's look and see what we've got. I've got a kilo, a newton. I've got a cubic meters in the numerator, a square meters in the denominator. So I've got a kilonewton meter. Yep, that checks, doesn't it? Okay, great. Let's do the SI units. Work out. It's got to be in foot-pounds force. Let's see. How about my pressure? I've got to be savvy enough to know that in my solution, I need to express pressure in pounds per square foot. So if I express my pressure in pounds per square foot times dV, cubic feet, let's see, I can cancel my units. I've got pounds force foot. Yep. Right-hand side of this expression for work exactly is the same as the units of the left-hand side. Okay, so what sort of a takeaway from your experience so far? First couple of weeks in class, first few weeks in class, it says that if I'm given a problem with a piston and cylinder, and I'm given the piston diameter in centimeters or the piston diameter in inches, I know I'm going to need to calculate the area for a free body diagram or something. I'm going to calculate that area in square meters or square feet, okay, so that I can get my volume in cubic meters or cubic feet. So that's a big key point of being very savvy and taking good use of your time in problem solving. Immediately change to feet, change to square feet for a area. Okay. Next thing is closed system. I'm sorry, just pardon me. You're still asked to find W out. However, you've got a problem that involves specific volume, not capital volume. How will you work through determining the work out when you're having to deal with specific volume? Let's see. The work out is the integral of PD capital V. I remember for a closed system that the capital V is MV, M is constant. I can pull it out of the integral. and then do my math work. So let's look at units for this type of closed system, quasi-equilibrium process where you're forced to work with little v. Okay. Left-hand side, work out, you know the drill. It's got to be kilojoules or kilonewton meters. Okay, we'll work on SI first. So M is going to be in kilograms. P, it's going to need to be in kPa or kilonewtons per square meter, and dV units. D little v, incremental change in specific volume, cubic meters per kilogram. And so if we study all these units, let's see, here's a kilogram in the numerator, kilogram in the denominator. Here is let's see, I've got a cubic meters in the numerator and a square meters in the denominator. So I've got kilonewton meters. Yep, that checks. You see how the same thing works with English units, but look, we'd better go through them. Left-hand side, it's got to be foot-pounds force. Work out foot-pounds force, mass, pounds mass, pressure in pounds per square foot, not pounds per square inch, times incremental change in volume, cubic feet per pound mass, change in specific volume, d little v, cubic feet per pound. So by inspection, you can see that the units are working out correctly. Finally, if you have a problem where you're asked to find, you're not given the mass. You're not given the mass in the problem. What do I do? And you're asked to find the work. And it'll say in kilojoules per kilogram. Okay. Here's what you're looking for. You're looking for little w, kilojoules per kilogram. You've got a closed system, quasi-equilibrium process, integral P d little v, pressure in kPa, dV in cubic meters per kilogram, same sort of visual study. And you can see that we're going to get kilonewton meters per kilogram. Well, that's a kilojoule per kilogram. Okay. And strangely, the English system is a little easier, isn't it? Left-hand side, foot-pounds force per pound mass. That's what you're praying for. If you use your pressure in pounds per square foot times specific volume change in cubic feet per pound, it's a little easier to see that you've got foot-pounds force per pound mass in your right-hand side units. Okay, so again, I've got to stress that units are just as important as numbers. And so here's the summary of the 3 slides we just covered, having to do with closed systems, trying to find the work for a closed system undergoing a quasi-equilibrium process. Depending on the type of problem, you may be asked for W out. 2 situations, one where you're working with changes in volume, capital V, or you may be working with changes in specific volume, little v. I hope now that you say, I feel more comfortable dealing with these situations. Sometimes in problems, you're not given the mass of the closed system. And so you're asked to find kilojoules per kilogram of work. That's little w, and you're satisfied to see how to work with that integral of P dV. Gosh, I hope this helps. I hope it helps you to put some things in perspective and maybe recap some of the homework problems you've had difficulty with so far. Okay, let's see. Now, units of little w for an open system. Okay, so as a reminder, let's see. Little w for an open system, kilojoules per kilogram. Hopefully I introduced that. And then W dot out over M dot is the definition of little w. So let's see if we can dissect the units of W dot out. Typically, it's given in kilowatts, so you have to remember a kilowatt is a kilojoule per second. I've got another typo, and so M dot is kilograms per second. That should be a little k, kilograms per second. Look how these seconds cancel out, so you're going to get what you're praying for on the left-hand side, kilojoules per kilogram. Units of little w out in English, foot-pounds force per pound mass. Same drill. You can see right out. What have we got? W dot out. It's got to be in foot-pounds force per second. You may do a little preliminary conversion to get your W dot out in foot-pounds per second divided by pounds per second, pounds mass per second. It's going to work. Or alternatively, you may be asked for little w out in BTUs per pound mass. Well, that's going to be, let's see, if you can get your result in foot-pounds force per pound mass, how will you get BTUs per pound? We'll just go to that conversion sheet, okay? Use unity, recognizing that 1 BTU exactly equals 778 foot-pounds force, and that way you can get to BTUs per pound for little w, which is W dot over M dot, for your open system. Okay, the last tip coming down the home stretch. Some students I'm finding, and correctly so, I fully understand. I also had this confusion until I worked through a lot of problems. What's the difference between change in capital KE and change in little ke? In other words, delta kinetic energy and delta little kinetic energy. And so it's the same relationship idea. So I'm hoping that you see a relationship between capital W and little w. So your intuition says it's going to have something to do with the mass of a system, if it's a closed system, or the mass flow rate, if it's an open system. But both of these variables refer to change in kinetic energy. So when we're speaking, when we engineers are speaking, we call both of those variables change in kinetic energy. So to some extent, shame on us, because you just got to learn the jargon. All right, so let's look at a little example. Delta capital KE and delta little ke for a closed system. Okay, this is the easiest to understand because it's right out of your book and probably out of your physics class, either in college or even back in high school. The kinetic energy of a mass, some sphere, the change in kinetic energy from state 1 to state 2. Let's say state 1 is a little velocity, state 2 is a big velocity. So it's speeding, this mass is speeding up, okay? And the question would be, what's the change in kinetic energy of this mass? Well, delta ke, you know this hopefully by heart. It's 1/2 m v squared 2 minus v squared 1, the change in velocity squared. I think you probably got this in your head. So let's look at the units of this delta capital Ke. It's joules. That's units of energy. A joule is a Newton meter. So let's see. A mass is a kilogram, and a v squared is a meter squared per second squared. We got to look a little closer to see if our units match. We can show this. Well, let's see. Let's take this meter squared and let's split up meter squared into meters times meters. And we'll pull that over to the left, to this side, and we're going to have kilogram meter per second squared over here times a meter. Okay, I remember what a kilogram meter per second squared is from the first day or two of class. That's a Newton. A kilogram meter per second squared is a Newton. So our units on the right-hand side is Newton meters. So we can show that delta capital Ke for this closed system situation has got units of Newton meters or joules. All right, so what's delta little ke for a closed system? It is simply delta capital Ke divided by the mass of the system. Okay, and so let's go through this units drill here. Delta Ke over M, well, that's going to be kilojoules divided by mass, kilograms. Right-hand side, meter squared per second squared. This is a little complex, so I've got a little note here. It says more about delta little ke later. Okay, so we're gonna get to that, but a kilojoule per kilogram is not equivalent to a meter squared per second squared. That's important to learn. What I need to introduce here is an open system. Back to our example, open system, steady state, steady flow. one inlet, one outlet. And let's say the velocity of this gas coming out of this turbine is a high number. It's V2. And what's coming into this turbine has got a velocity of V1. Okay. And so I'm going to suggest that the little ke, little kinetic energy, is, oh, pardon me, I got ahead of myself. The definition of the change in little kinetic energy, little ke, is 1/2 V2 squared minus V1 squared. So this just sort of accept this as a definition. Delta ke for an open system is 1/2 V2 squared minus V1 squared. And we've got units of meters squared per second squared or feet squared per second squared. And so in open systems, similar to closed systems, we need to have delta ke in kilojoules per kilogram or BTUs per pound mass or foot-pounds force per pound mass, because when we're working in open systems, we're typically working with the first law of thermodynamics. And that first law for open systems involves properties with units of kilojoules per kilogram or BTUs per pound mass. So that's my little remark. We got to do a little more derivation of getting these units straight for the change in kinetic energy for an open system. But I do want you to see that delta ke, very similar for an open system and closed system in terms of units. Okay, and so now we're going to get into trying to get this meter squared per second squared thing right, get a full understanding of how do we convert from meter squared per second squared to kilojoules per kilogram. And this is my own scratchy handwriting when I was coming back and I was teaching and trying to communicate to students, how do you do this? How do you make this conversion? So here's what I did in my writing. I wrote down 1 kilojoule per kilogram. That's my starting point. Okay. So, well, what's a joule? Well, a joule is a Newton meter. So now I've got kilonewton meters per kilogram. Well, what's a Newton? A Newton is a kilogram meter per second squared. So now I've got this sloppy mess. Look at that sloppy mess. Can I, let's see, can I cancel things out? I think I can. I can cancel a kilogram and a kilogram, and I can combine these two meters together to get a meter squared. And I've got a second squared down here, but I've got this pesky little k here. Little k. That's kilo. That's 1,000. That's 1,000. Okay. I hope that I've shown you that I've derived the relationship between meter squared per second squared and kilojoules per kilogram is this. Unity equals 1 kilojoule per kilogram divided by 1,000 meter squared per second squared. That is the conversion. Now, I did a terrible job in class explaining this to my students face to face, but I'm hoping I'm doing it a little better on this video. So this is something you got to get in your head. You're going to be doing it a lot through the rest of this course. The conversion of meter squared per second squared into kilojoules per kilogram is this expression for unity. Okay, let's look at English. English unit for kinetic energy terms. And typically we want to get our delta ke in terms of BTUs per pound. So this can be complex. This can be complex. So delta little ke is 1/2 change in velocity squared. And we want our units to be BTUs per pound mass. And with our calculator or in our written work, we've got feet squared per second squared. How do we convert that? We have to go back and we have to leverage our experience and knowledge with this conversion factor page and our experience working with this unity trick. So let me guide you through it. We're going to go and we're going to look at this expression of unity. 1 pound force divided by 32.174 pounds mass feet per second squared. Got that out of the conversion factor sheet. So I'm going to put it in there. Okay. I'm also going to put in, I need BTUs per pound. So I better find another conversion where this got BTUs in it. So here it is. 1 BTU equals 778 foot-pounds force. So now, okay, now visually, help me go visually. Feet squared per second squared, pound force, BTU. Okay, at least I see this cancels with this. Okay, got it. Oh, here's a foot and a foot. So there's a foot squared that cancels with the numerator. Okay, and then sure enough, the denominator second squared cancels. So I'm left with BTUs per pound mass. And so here is the way to convert feet squared per second squared into BTUs per pound. Now notice here in the video, I'm not saying simply divide by 32.174 and divide by 778. That's not good. You really must show these units canceling in your engineering work so that you can do this over and over again without making the mistake of multiplying by one and dividing by the other. And this is the voice of experience talking. I've done that before numerous times, and I've gotten burned for it, worse than just grades. So this is critical to write out your units as well as your numbers. Okay, and so here is the summary of kinetic energy units of the V squared units. Here's my term for change in little kinetic energy, specific kinetic energy, 1/2 V2 squared minus V1 squared. That's the expression for that. I got to work, here's the summary. SI units, basically, I'm going to divide meter squared per second squared by 1,000, okay? But I am going to write out all my units. In English, I end up with feet per square per second squared in my governing equation, my fundamental. But I don't have my units right because I've got BTUs per pound in other parts of my fundamental equation. Got to convert feet per square per second squared into BTUs per pound. And here's the conversion. So that's the summary of kinetic energy. That's the end of tip 5. And that is the end of the tips that came to my mind to try to help guide you along as you go through the rest of this class, recognizing that units are just as important as the numbers, both in terms of engineering work and getting your analysis and or design correct, and also getting a good grade in the class where you want to get full credit. You don't want to just get partial credit and get dinged where you just didn't have your units correct. So I hope that helps. And I encourage you to keep working with your units, writing units down as you work through your solutions.